let's let f of x, y, z be a vector field, and it has components p, q, and r, all functions of x, y, and z. Now, okay, I've presented f as if it's a vector field in space because it has three inputs, x, y, and z, but it just as easily applies to a vector field in the plane where it just has inputs x and y. And the usual stuff has to be true to make everything well behaved. The p, q, and r have to have continuous first partial derivatives in an open connected region R. And let C be a piecewise smooth curve in R. So this guy are different. Anyway, good to point that out. Connected just means, you know what open means. Connected just means that between any 2 points, you can make a path between them, a curve. The following are equivalent. What does that mean? It means statement A implies statement B, and in reverse. So you could use that double arrow we talked about earlier. And the same for C. Statement B implies statement C, and going backwards, C implies B, which means C also implies A because both these sets of arrows go both ways. So any one of those is true. Any one of those three statements is true. Any one of the other statements is true. That's what we're saying. The following are equivalent. Does that make sense? Okay. First one, A, f is conservative. What does that mean? There exists a scalar function, lowercase f, such that del f equals uppercase f, the vector field. A, f is conservative it's equivalent to saying that the line integral is independent of path, the line integral with respect to the vector field. Well, we kind of already knew that, right? What is that? At least going in the forward direction? That's the fundamental theorem of line integrals, right? If f is conservative, you can use little f and the fundamental theorem of line integrals to evaluate it taking f of the endpoint minus f of the beginning point. The curve in between doesn't matter. So at least going from A to B, we already knew that. But then also you can say that if either A or B is true, and this is the weird one, the integral over C of f dot dr equals 0 for every closed curve C in R. So what am I going to show today? Well, okay, I already showed A implies B. I'm not going to show B implies A. It's in the book. It's going to take too long, so we're not going to do it. So I'm only going to prove, I could show B implies C or C implies B. I'm only going to prove one thing. I'm going to prove C implies B, okay, to give you a flavor of why that last statement might be true, at least going in one direction. But actually, you can reverse this little argument, and it's pretty easy to show the other direction. So I'm going to show, okay, notationally, I'm going to show statement C implies, so using one arrow, I'm going to show that C implies B. I'm going to show C implies B. So what can we assume is true? I'll put this in brackets because this is the assumption. We can assume that the integral over C of f dot dr, this is the statement C, equals 0 for any closed C in R. We can assume that. So what do we need to show? We need to show C implies B. We need to show B. So what is that? We got to show that it's path independent. So how do you do that? Well, you pick two generic paths from a beginning point to an end point and show that you get the same thing if you evaluate the line integral over each path. All right, so how do you do that? Let's say we have a beginning point, call it capital A, an end point, call it capital B, and just drawing a picture for you to kind of get you going here. Let's say that we have a curve, just a generic curve, C1, going from A to B, so the orientation looks like that. and we pick another kind of random generic curve. And I'm not going to, you could do it if C2 crosses C1, but it becomes much more complicated. So I'm going to leave that detail out. And so this is C2 in yellow, and it starts at A and ends at B. Okay? So notice that I picked these generically. Okay? C1 and C2 can be any closed curve. And I'm not writing all that down, but in a real formal proof, you would say that. So, all right. So keep this picture in mind. Notice that if I take, oh, you know what would work better? If I label the bottom one C1. Now, it doesn't matter. I could have got it to work either way, but this will work out better. So notice that together, C1 and the oppositely oriented version of C2, negative C2, forms a closed curve. Huh. Maybe we could use that. What do you think? Yeah, maybe. Okay, so let's do this. Let's take the integral over C1 f dot dr. Excuse me, let me make that integral over C f dot dr, where C is going to be the union of C1 and negative C2. Where C is going to be the union of C1 with negative C2. Oh, and by the way, what can we assume about that? What can we assume about that? Look at the thing in red. It equals 0. I'll put the 0 right there, if that's okay. Okay? Does everybody believe that? Nothing too crazy yet. Okay, help me out. How does that split up? You're exactly right, but I'm not even going to show in the nitty-gritty details here, so I'm going to make this negative C plus negative C2. And you've already seen this trick once today, right? So you can think of the integral over negative C2 f dot dr as the opposite, excuse me, of the integral over C2. Okay, and that's going to be the heart of the so-called proof here. It's not really a formal proof. We'll just call it something to make you believe it. Okay, does everybody see what I did there? Everybody okay with that step? Now on the left, what does all that equal? It still equals 0, so I'll throw that in here. Still equals 0. So what's your conclusion if you isolate the integrals on either side? Yeah, so think of just adding this guy to both sides. I'll have it in the wrong order, but it doesn't matter, it's the same thing. So we get the integral over C2 f dot dr equals integral over C1 f dot dr. I chose C1 and C2 arbitrarily. So that means that B is true. The integral is independent of path. Do you buy that argument? Okay. So I guess I should at least conclude that. So since C1 and C2, I'll just say are generic because it's hard to spell arbitrarily. The integral over C f dot dr is independent of path or path independent, same thing. But I like that proof because it really, if I didn't show you that, it'd really be, the first two, A and B, are believable that they're equivalent, and then the third one seems to come out of nowhere. But that kind of gives you, if you understood that, that kind of gives you an idea of why it's true.